On the which plane? On the xz plane, right? On the xz plane. And on the xz plane here, z is just equal to what? 5 minus x, right? So what's that look like? It's got a slope of, yeah, so let's go up 5, right? 1, 2, 3, 4, 5, like this. And when x is 5, z is what? 0. So you connect this like that, right? And then what happens as you vary y?
Just shifts that line
Yeah,
that way, yeah.
exactly. So you end up with,
The ramp.
it is a ramp.
There we go. A better description of that is an inclined plane.
Well, it's a ramp because you're doing the volume of the solid. So if you want to describe the solid, yes, that the roof would be an inclined plane, sure. So what's the height of this thing? 5. What's the base? 5. And what's the depth?
3.
3, right? So you can say this as one half of
25 times 3.
75 over 2. Nice. Yeah. They just want you to be able to graph that. They want you to be able to go from the integral expression.
So we need to graph.
Let's say I fix an x value. Let's say I fixed it right here, okay? So I'm looking at this slice right here. So here's the slice I'm looking at. If I wanted to get the area of this slice right here, I would fix the x value. I would integrate from c to d and do it with respect to y. If we want the volume of this entire shape, what are we going to do with this slice? We're going to move it forward all the way to b. We're going to move it backward all the way to a. Each slice is its own integral. How many of these slices are we adding up? A whole lot of them, an infinite number of them. So in order to add up an infinite number of things, instead of adding up an infinite number of rectangles, we're adding together an infinite number of slices. Each slice in itself is an integral. So we will find out what the area of each slice is in terms of x, and then take this and go from A all the way to B. We'll slide it forward. Now, can you switch x and y here? Could we take a slice? Could we fix y instead? For example, could we fix the y value here and look at a slice that looks like this instead? Sure. We could fix y.
You went to the wrong point. You're supposed to go straight down.
Great, congratulations. You understand it, you see it. Don't need to nitpick it. Do you understand what I'm trying to do there with that slice? With that slice, I'm fixing a y value. So I'm writing the area of each slice in terms of a y value, and then I'm integrating from c to d. Will the volumes be different? No. It's the same idea. So it's basically, instead of chopping up a solid this way, you're rotating 90 degrees and chopping, making the slices perpendicular to the original ones. Should it matter how you slice it up?
No.
No, in fact it doesn't. What does the integral become? With respect to y. Shuhan, tell me. So you have 1 over 2 x squared y squared, right? From what to what? 1 to 2. And remember, we still have this on the outside, right? We're not going to take care of that yet, but just remember that it's there. Remember that we just integrated with respect to y. So what are we plugging the values 1 and 2 in for? Y values. You're plugging them in for y values. So if you plug this in for y values, please let me finish, x squared 2 squared minus 1 over 2 x squared 1 squared. So what do we end up with? 2x squared minus? Thank you. So what do you end up with? 3 over 2x squared. And now you're integrating that from 0 to 3 of dx. So if you integrate that sucker, what are you going to end up with? 1 over 2x to the third from, and that's going to be 27 over 2. Yeah, that's exactly it. So if we do this one, should it matter? Oh, wait, is this the same thing?
No, it's a different order.
Ah, are you sure? It's this. Okay, excuse me. It's a different order, but what? Why is it the same?
Same solid.
It's the volume of the same solid. What key thing did they have to change? In addition to changing dx dy, what else did they have to change? They had to switch the limits there. Do you see that right there? 0 and 3 are now on the inside. If you didn't switch that, would it be the same? It might be. Who knows? It might be one of those cool things, like if you take this part or this part, it might be the same.
There's no guarantee.
There's no guarantee. Should this come out to be the same thing? Yeah, it absolutely should. So if we integrate with respect to x first, what do we get? x cubed y from, and we're plugging in for what? We're plugging in for x, exactly, right? So we have 1/3 3 cubed y minus 0, right? Is that okay? So what do we end up with? 9y, and we're going from 1 to 2 dy, right?
Yep.
So what do you end up with? 9 over 2 y squared from 1 to 2. So end up with what? 36 over 2 minus, which is? Does it come out to be the same thing? Yes. This specific fact that you can integrate these in either order has a specific name. Fubini's, I think it is. Where is it right here? Fubini's. Yeah, good. I got it right. This is one of the rare times right below this, and I'll tell you, you don't have to check out what it says about the proof. Do you believe that that should be true? Because that's good enough at this point. You do not need to prove this. It actually, in the book, it says it is too difficult for us to prove this in multivariable calculus. So you can prove it later, but essentially it just means you can integrate within either order. Certain ways will be easier sometimes. So most of the time, though, is it going to matter? No, it's not. Yes, Josh. Set up the integral. So I'll do these two integrals right here, and we have y sine xy. That's true, right? Which one do you want to do first, dx or dy? Dx first? Is that good? So if it's dx first, it's going to go from 1 to 2, and then it's going to go from 0 to pi. You can't do 0 to pi first. 0 to pi, this is the x, and this is the y. Ooh, right? Are we okay? I'm not derailed yet? So if I integrate this with respect to x, what do I end up with?
Negative.
What? What happened to the y?
Because it got because
I understand. Let's just do the whole thing out here. Hold on. So it's negative cosine xy times what?
1 over y.
Y.
Oh, then I need negative.
Because it's a constant, it comes out.
But why is it 1 over y?
Why is it 1 over?
Why is it 1 over y?
No, just y.
Isn't it just y?
Just y. It's just y squared.
but
No.
there was a y before that, so
I'm confused. We're integrating this thing with respect to x, right?
Sine of 2x is
What?
negative cosine 2x over 2.
Excuse me. We're not differentiating. What are we doing?
Integrating.
Integrating. Okay. I see. I see what you're saying. So what's this going to become?
negative
Negative.
cosine.
Y cosine xy times 1 over y. Because we're integrating this. So what does this simplify to? Let's just go to the simplification. It gets the negative cosine of.
Y.
Because if you differentiate this with
From 1 to 2.
if let me finish, please. I differentiate this with respect to x. You end up with y sine xy. If you differentiate this, you end up with y sine xy, which is our goal.
Oh.
Yeah. And we're doing this from what to what? We're doing it from 1 to 2. So if we do this from 1 to 2, we end up with negative cosine 2 what? 2y minus negative cosine y. So you end up with cosine y minus cosine 2y, correct? And now you're integrating that from 0 to pi with respect to dy. Did you fix your double y problem now? Yeah, you fixed it. Can you integrate this cleanly? Yeah, so the integral of cosine is going to be sine y minus what?
1 over 2.
The harmony, I can't follow you. Sine 2y, correct? And you're going from what? 0 to pi. So you have sine pi minus 1/2 sine 2 pi minus, I understand 0 minus 1/2 sine of 0. What sine is 0?
0.
So that whole thing is
0.
0. Great. What sine of pi? Minus what?
0.
1/2 of 0. So you end up with
0.
0. Do you want to check to see if that makes
Let's do it.
even a little bit of sense?
Yes.